Well, we're ready to consider design of digital filters, having gotten the background. Now, I was going to lunch with Jim Kaiser, and he was telling me all kinds of various methods. And one day he put this on the back of one of the mats at lunch, and I said, "Does it always work?" He said, "Yes." I said, "Why did you tell me the other ones?" Well, people have to show off how much they know. You will find in many talks you receive, the speaker is showing off how much he knows and is not really trying to communicate with you. So I threw all the other methods out and said, let's do this. So let me discuss the method. Here is the design you want. There's positive frequencies and negative frequency, and we're working a complex notation. Now, last time I closed with the observation that if I expand this function into complex Fourier series, the coefficients, which I've drawn here, but they're complex numbers, but I've drawn them as if they were real, those coefficients are the coefficients of a digital filter that does that job. The trouble is there's an infinite number of coefficients. So you have to truncate. Now when you truncate, you have the Gibbs phenomenon. So you window, and then you have a reasonably decent filter. The ripples of the Gibbs are cut down by a factor of roughly 10 or more, depending upon the window. So you can see how simple it is to design. There are only two difficult things. One, what end do you pick? And two, what window do you pick? Well, Kaiser did something more than this. He tried to answer those questions. And so what he did, and I'm recommending you the method he used, he designed a filter, a bandpass filter, with a bounds this way of size delta and transition zones delta F. And he wanted the signal to stay inside that bound. So he gave two numbers, A and delta. They determined. Well, what do? You calculate minus 20 log of delta, then you calculate n, the number of terms, which is this. Now let's look. Delta goes through a logarithm to here, but delta F appears right here, and you shrink delta a bit, and n goes large, right? Clearly, it's easier to squeeze this way than that way for the number of terms, right? Now you know the number of terms is an integer. It's got to be an integer. Now you calculate an alpha. Here's a formula this way, this way, this way, and let's look at what it is. If I take 8, well, we'll say 9, 18, 27, and so on. At 8.7, after that point, above 21, it's going to be 0. This is a straight line pointed for that point 8.7. So it's a straight line coming down this, coming down this way. On the other hand, at 21, it's 0, so it's coming down and it's going to go like that. So this function looks like that, and it's 0 across here. Given that, depending on what the A is, you pick one of the three formulas. You calculate the C, the CK, provided you got a band pass, band stop, little small changes. Then you window with this peculiar function. I0 is the Bessel function of pure imaginary argument. And there's the K for the term, there's the n number of terms you took, and there's an I0 down below, and I0 is simply this power series, 1 plus x over 2 to the nth n factorial all squared. It's sort of like an exponential, but the terms in the exponential series are each one squared, right? It looks roughly like e to the x over 2, but it's squared. And the simple recursion formula with the first one 1. So I0 is very easily calculated by the simple recursion formula. Given an x, and a subroutine comes out, you evaluate here, you evaluate there, and you're in. Now let's go back and see a little bit more what happens. I first asked him, where did he get the 0.4 for that term? Well, he said, I ran off a large number of ones, I measured them, and for various arguments I found these were kind of formulas. He said, I tried 5/10, it didn't work, 4/10 fitted very well, so I quit. What he did was a combination of theory and using a computer to get a formula. Now, Kaiser's formula works very well, except for a couple of difficulties. Once in a while, see this edge, he calculated for a single edge. There's 2 edges in a bandpass filter, and there's 2 more over here on the negative frequency, so there's really 4. The ripples induced by those sometimes work together and show a bigger error in the delta than you planned for. So what you have to do is cut the delta down in size and repeat. Once in a while, I say the ripples will be bigger than they should be because of the cooperation ripples from this edge, this edge, to that edge. But that's no great trouble. You repeat once, but you don't have to repeat it 10 times. It gives you both the n, number of terms, and the window. So let's look at that window. I0, I said, looks something like e to the x squared, only going a little faster. As when k is 0, this is I0 of alpha, divided by I0 alpha, is 1. When k is n, this is I0 of 0, it's 1, you have 1 over alpha. 1 over I0 of alpha. And it looks something like that. It looks like a Hamming window, a raised cosine of platform, so long as the alpha is, got some positive. When the alpha is 0, of course, over here, all this whole range, then you have the Lanczos window. They're all the same size, there's no shape. So you know what window to use. It's easy to calculate the whole thing. But let me dwell on this. More and more we are doing what Kaiser did long ago. We use the computer plus theory to get some semi-empirical formulas. Now I could go in more of that than I really want to if you care to keep on talking endlessly about it. But it's a very practical method. Now I have to turn to a next thing called the finite Fourier series. The Fourier functions, sines n theta and cosine n theta, were orthogonal over the 2 pi interval. That they are also orthogonal over a discrete set of equispaced points is a miracle. They are the only orthogonal set that does this. But the Fourier series are orthogonal over a discrete set of points, typically 2n. And you'll have a 1, you have a cosine, sine x, cosine 2x, sine 2x, cosine n minus 1 x, sine n minus 1 x, and a cosine nx. After all, 2n points can only determine 2n functions. And you have the 0 and the nth case here where this is oscillating. The sine would have been all zeros at those equispaced points, putting in pi's and so on where you want. So these things are orthogonal over a discrete set of points. It assumes the function is periodic. But there's a miracle that it is. Now it would appear, well, the coefficients an, let's call them an, is 1 over n summation. The data times the cosine of, call it k, n, x. No, x, n. There's a sum of products right here. And there are 2n coefficients, so it looks like 2n squared. I got to do this for every one. 2n sum, 2n terms, 2n squared. Roughly, that's the amount of multiplications and the amount of additions I have to do. Looks like a lot of work. Well, I'm going to tell you a story now which is embarrassing to me, but I hope that you will think it through very carefully what happened. You've all heard of the fast Fourier transform, right? And you may have heard it called the Tukey-Cooley algorithm. Well, I was computing for Tukey. I had a card program calculator. Tukey essentially suggested to me the idea. Now, the idea is very, very simple. There are two ideas. One is, if I'm going to multiply by cosine, there are, even in a simple one, 4 values which have the same cosine value in the interval for the lowest frequency. Higher frequencies, there'll be more. Therefore, if I were to add those function values first and then multiply, I will save a lot of multiplications. Right? Right? Secondly, a very simple identity. Cosine 2x is 1 plus, cosine x is 1 plus cosine 2x over 2, cosine squared. From the square of a cosine, I can get a higher frequency. From the cube, I can get the higher frequencies. Therefore, multiplying values together, or jointly, can save me from looking up the higher cosines. Now, both these ideas were in a book I wrote and had written, was very readily available. But I had a card program calculator. Now, if you know the process of the fast Fourier transform, there's a butterfly operation, which you have to disconnect. Well, I would have to pull the cards out of the machine, sort them, put them back in, run them through, pull them out, sort them, so and so. Couldn't possibly afford to do it. So I decided that was one of John's foolish ideas. Time passes. He suggested to me again, this time I got a 650 internally programmed machine. All I remember is it was a bad idea, so I don't look. I didn't do the Tukey-Cooley algorithm. Why? Very simple. I had been right when I could not do it. Later on, I forgot that I had passed from one type of computer to another. I had forgotten there had been progress. I merely remembered it couldn't be done. This is an extremely common mistake. You see it again and again and again. The experts with analog filters told me things couldn't be done. Well, they couldn't be done with analog filters, but it could be done with digital filters. I have heard many, many times something cannot be done when they're wrong. It is evident that any proof that something cannot be done must rest on a lot of hypotheses. My hypothesis, my proof that I couldn't afford to do the thing for the way Tukey wanted, rested on the assumption I had a very low capacity computer. It was false the moment I got a better one. I say this very much. I'm very much annoyed by my experience. I don't take it kindly. Nevertheless, it's not the only time I've made a mistake, but it's the really best serious one which you can appreciate. So I want to dwell on this point. When you decide something is impossible, and years later somebody says, don't glibly say it's impossible. Go back through the reasons. Are they still true? Conversely, if some senior officer tells you something cannot be done, ask yourself, does he know he got the present weapons? Was he right when he thought it through years ago, but is he making this same bad mistake? Progress consists of showing the great many things that could not be done are now possible. And it's a very, very common mistake. And I told you the story to get it across to you. Not make that mistake yourself. Well, what does a fast Fourier transform do? It reduces this number to roughly n log n. Now, that doesn't sound a lot until you say, well, suppose there are 10,000 data points. N squared is 100 million. N log n is not bad, right? It has made many, many areas of computing practical. Many areas of science became practical once we got the fast Fourier transform. Now, it's been my better experience in general in computing that when you find a real trick method of computing something, the round-off errors are very high. So I promptly investigate this, and the answer is no. Because the computing is less, the coefficients are actually more accurately known than they are with the standard method. For once, a nice trick method produced a far better answer, more accurate, with much less computing time. So it's a very, very nice thing, but we have to be careful. What does this do? Given a function which may be periodic, but there's a delta t of sample time, and there's an n samples, 2n. That is the interval of periodicity. Now, of course, that means that instead of having this, I have, which means that what I am doing is I'm forcing every non-harmonic. What do I mean by harmonic? It fits exactly repetition within the interval. What interval? The delta t of the time measurements times the 2 endpoints, whatever n picked. You are forcing every frequency to fit that, either be a fundamental or overtones with that. Frequencies which are not will be spilled into all other frequencies. And you can work out the formula very easily. What will you see for a sinusoid that is not harmonic? You'll find it's very mainly spread around nearby, but it's spread over the whole spectrum. It isn't what you think it is. When you use a fast Fourier transform, you are asserting this function in this interval is periodic. Those choices you made there may have very little to do with the periodicity of the signal. Very, very little. You're getting something rather different from what you thought. The fast Fourier transform does not give you the Fourier coefficient of the Fourier expansion as a Fourier integral. It contains this very, very definite statement. Everything shall be periodic in this interval here, which had nothing to do with the data, practically. Everything is forced to be periodic there, and what you see is the result of that forcing. It's not the original signal at all. Now I have to take up next the topic of the spectrum, which is another very, very difficult problem. You may remember that AK squared plus BK squared was a pure number. It didn't matter where you put the origin, you got the same AK squared plus BK squared out of it. Put the origin of the Fourier series anywhere you want, you always get that, or if you want CK squared, or if you want CK C minus K, if you are dealing with real functions, which you are. So the spectrum is either this or this, and the spectrum is independent of the origin. But for the 2n coefficients, I only get n, or n plus 1, values in the spectrum. The spectrum will look like out to the Nyquist interval. And of course, it's the same on the other side, since I'm using the complex exponentials. But there's going to be n plus 1 points there when there were 2n values CK, AK, and BK, or CK and C minus K. You're losing all the phase. That's almost half the information. Nowadays, you are more familiar with phase-sensitive signaling systems, phase detection, such as phase modulation instead of amplitude. In the early days when I first learned this stuff, it was much more amplitude. I could see they're throwing away half the information, but it was customary. You know why? I looked into the matter. It's a very simple reason. Why did we blunder? The telephone company early found out that the phase of the frequencies I'm speaking to do not register on you very well. They're phase insensitive because, reason, as I speak, the various frequencies propagate through air at various velocities, so they don't, what I emit in one phase do not maintain the phase relation. And if a hearing is going to work, it's got to work for all kinds of distances. Therefore, evolution gave you an ear which is not very phase sensitive. telephone company found phase doesn't matter, throw it out, look at the amplitude, that's all that counts for voice, to a great extent. Now, it wasn't true. I got involved in the hi-fi system merely because I wanted to learn a little about electronics, and I thought I'd build myself a couple of hi-fi system out of Heath kits to learn electronics, and in the process I learned a great deal about other things. Because the telephone company said the phase is not important, they started producing more and more exquisite hi-fi amplifiers, flat gain across, but good musicians could tell the difference. And they finally came around to the fact that the human ear does, to some extent, detect phase. And so they began to have to pay attention to phase as well as amplitude. But for a long while, they kept on trying to build better and better amplifiers by merely controlling the amplitude instead of paying attention to phase. So there's a general rule. The human ear is very insensitive to lots of things in the sense you can get the message through. All you got to do is go to the airplane cockpit sometime and listen to the noise that goes on there, but the pilot can understand it. On the other hand, you've only listened to a skilled musician to realize what finest discrimination the human ear can do. It can both get through vast amounts of noise and it can make very fine discriminations. And so when you're dealing with a matter, you've got to ask, which of the two am I in? If I'm in a hi-fi trying to fool the human, I've got to pay a great deal of attention to phase and so on. If I'm not in that position, I can pretty well dump a lot of the phase and pay attention to the amplitude only. Now, the spectrum has been very, very useful to us. It is what Bohr and other people did to find out what the inside of the atom was. From the spectral lines, they tried to deduce what on earth went on inside. It's played a big role in trying to deform quantum mechanics. I took over a thesis one time when the professor and the student got in a quarrel, and it was an attempt. Given a black box, which you can put a signal in and you measure the outputs, can you determine the structure of what's inside from putting signals in? And the answer is, within a reasonable degree you can, but you cannot do it exactly. There are different equivalent structures which will sound exactly the same. Just as in electronics, there are different circuits that will have exactly the same response. They nevertheless may not have the same topological structure. Nevertheless, you can tell a great deal about what the black box probably is, and it's what you want to do. Given a chemical plant that's working, you don't understand all the details. You'd like to understand it better. So you shove in more or less white noise, and you look at the response over here, and you study it, and you construct a model of what the chemical processes are going on inside the chemical plant. It's a very useful technique. When you don't know what's going on inside, the spectrum is very useful. But I told you it threw away half the information. But I've got to tell you more things. It's awful. One of the early stuff I did for John was the spectrum for interception or detection or whatever you want to call it, the radar data for guided missiles and so on. How much information is where? Well, one of the things we got was the spectrum. Now the spectrum is the amount of energy at a given frequency. Something like that. Symmetric. If, however, I remove the mean from the data before I start, which is a common thing statisticians do, that point is brought down to there. Well, because the airplanes were flying ranges past radars, John had me take out linear trends and sometimes linear parabolas. I mean, parabolas, not linear straight lines. And every time I returned it and gave him the answers, I said, John, this is the spectrum of the difference between the straight line and the data. It's not the spectrum. Because while Fourier series is linear and you can add two signals to get the sum, the spectra, which involves squares, the spectra of the sum is not the sum of the spectra, right? For example, take a signal, an exact negative of it. The sum will be 0, but the spectra will both be the same. Right? So when you add two signals, there's a chance of cancellation. You can't add spectra. I kept on pointing this out to John, that I did not allow for anything for taking out the trends and so on. One day he turned to me and said, "Shut up, Hamming," which I took to mean he didn't know what to do either. So I quit needling him on it. He told me, "Shut up," I shut up. But I have watched ever since then for an answer. Now I told you, if you just take the mean out, you'd lower that. If you now window it somewhere along the way with a von Hahn or a Hamming window, let's put it in red so you'll see what happens. This point will come up, this point will come down, and you will have pretty much the same after that. Well, I saw that thing quite a few times in our Whitney location. After coming here and looking at these things more, because I tell you, when you're in industry, there isn't a time to think because there's a lot of pressing problems, but a university professor is supposed to think, so I thought, and I realized that I had seen this thing, and I'd heard words like, well, most of the energy is about the third frequency out. Hell no, it was there, and the way we processed it made it that way. They interpreted the result of processing to be the original source. Now this you have to realize. I earlier, 2 lectures ago, said you look at everything through a window. You process data. So let's look at the whole data processing process to see what happens to you. There's an ongoing phenomenon. You turn your equipment on and off, and I'll simply put it about the origin symmetric. You turn it on and off. That means you're looking at that through a square window. Or if you want, boxcar. And you remember I derived a sine n plus 1/2 x over sine x over 2. And asserted every line in the spectrum here, every line of that spectrum is smudged by that. A pure line now becomes, the longer the record, the narrower. But every single line in the spectrum is smudged because I took that out. Now I sample. Bing, 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 bing. I'm aliasing, right? Now the original one had a spectrum like that. Once I alias, those are folded back and forth, and so what I see is not that spectrum, but I tend to see something pretty flat here and something there. That's what I will see because of two effects. The finite length, which smeared things out, and the aliasing, which brought it back and forth. So one typically sees, not always, one typically sees a signal at low frequency and pretty flat out there, what we call white noise, all frequency equally likely. Well, what can you do? Even if you want only low frequency signal, what one often does is oversample. If I oversample much more than I have here, then the folding frequency, say, would be twice as far out. The signal is now like this. I can remove more of the noise if I oversample, and then use a low frequency filter to cut off this and remove all that noise. So one often oversamples, knowingly, much well above what you need to do to try and remove the errors of the measurements of the instrument. And then you filter, remove the noises above that point, and you then have the signal freed of much of the noise. But there is no linear method which will separate the noise and the signal in the same band. There is no linear method. Now I want to stress linear. This is a very, very common mistake. Oh, in the 40s, when power spectrum began getting started, Merrill Lynch and some other people paid the bill to have some people analyze, and they found out that the stock market prices were essentially white noise, flat spectrum. Well, the assertion, there's no knowledge. Therefore, the point chart guys can't be doing anything. Mind you, I'm not saying they are, but let's consider two flaws. One, the spectrum removes all phase. Two, they're assuming the thing is linear. Fourier analysis assumes linearity. If the stock market is not linear, that analysis tells you nothing, correct? I've seen that regularly. I saw a tremendous amount of money spent on a project trying to anticipate when a carrier deck will come up or down due to waves. Because the pilot landing would love to know whether it's going to go up and slap him or it's going to drop out from beneath him. They tried modeling by Fourier methods, which assumed that the sea was linear, but it isn't. And the more they worked, the less they got. I kept telling them, but you don't really believe that the stuff is linear, do you? Why do Fourier analysis? Their answer was, we don't know what else to do. So they spent millions of dollars on the project and got essentially nothing out of it because the thing wasn't linear. Fourier analysis implies linearity of the underlying mechanism. If the underlying mechanism is not linear or close to linear, what you get is not going to be relevant to what you want. So it's very valuable in linear systems, but we're moving more into nonlinearity, and it's not going to do you too much good to try and do linear analysis. The stock market, come back to it since you people are always interested in it. It's not that the stock market cannot perhaps be predicted. It's not going to be done by linear formulas, because linear formulas probably have no information, although they threw away the phase. You probably could reanalyze the thing in phase and amplitude, and you'd find probably very little information. The difficulty of the stock market, which picks you and me, is that it's not honest. And you as an outsider are at a disadvantage. And if you take advantage of inside information, you are illegal. It is strictly stated. You may not take advantage of inside information. For example, illustrating both parts. I was on a board of directors many years ago, and we were going to split the stock. And in those days, maybe you remember, you were much younger, when you split the stock, within a couple of months, the stock was back to original price, so you doubled your money by splitting the stock. It's a remarkable business. Nobody understood it, but the stock market responded by just raising your price back up to the original price. So stock splitting was a good way to double your money. Well, we had a discussion on we were going to do it. Why not? The lawyer said, now, careful, he said, as you leave, you may not tell anybody, you may not act out or anything else until the official announcement day, so and so and so and so. So I behaved myself. Next board meeting, I come in, I'm standing next to the chairman, who was a very smart guy. I looked at us people, I said, I don't think these people necessarily blabbed. They probably kept their mouth shut. But it's perfectly obvious that the information we were going to split the stock got out before the split. He said, of course. I said, what do you mean? He said, the law requires us to go to one of 3 or 4 printers and print the prospectus. The printers, the moment they get a prospectus, run off another copy and run down and hand it to the broker. The mark is crooked. But you can't do it. You can't do it if you're going to be honest. So it's not a game for amateurs to get into. Not at all. Even if you think you can do it with machines, don't do it. Well, I wanted to get enough more on the next topic. When I started this topic, I told you I thought I knew nothing about digital filters. I thought I was ignorant. I wasn't, but I didn't know I wasn't. Years and years before, when I had been forced into studying trajectories, and I told you about the frequency approach, I analyzed predictor-corrector methods because they were the most useful ones. They gave me a control and accuracy, and they were the most efficient ones, as against Katarunga and other methods. And there were several of those around, and Hamming invented another one along the way. There were quite a few to play with. What I did not know when was that I was in a corrector dealing with a recursive digital filter. But you see, since I was doing it differently, I came up with different definitions. They had defined a filter to be one which a bounded input gave a bounded output. Now you can see why they would do this. With electronic analog gear, if the input is bounded and the output isn't bounded, you're going to melt the thing down. But on a digital filter, you'll just overflow, which is quite a different thing. I realized that wasn't working. I want to integrate. If I want to integrate a constant, a bounded input, what's the output? A function proportional to t, right? And it's going to be unbounded. Nothing I can do about it. A bounded input will not give a bounded output, so I thought I'd do some more thinking about the matter. And then I came to the problem in spaceflight of trying to land on the moon in the early days. Now the moon has got no atmosphere. There is no drag. Therefore, if you have an error in velocity, it goes up like the square. I'm sorry, you get an error in velocity, it goes up. And the errors go up quadratically landing on the moon because there's no drag to bring it back to reasonable. You see, if you come into the Earth too fast, the friction will be higher and will slow you down. If you come in too slow, the friction will not be as much and you'll be going faster than you calculated. So there's a focusing effect coming in the atmosphere. There isn't on the moon. So I found out that the error could grow quadratically. It could depend upon n squared because there were a double root in the difference equation. So I said to myself, you know, at first I was alarmed by it, but after a while I found out why it had to be and thought the physics behind it. Yes. A second order differential equation integration is a digital filter when you really look at it, but it's going to grow quadratically. What I'm going to have to do is change the definition of what they mean by stable from bounded input, bounded output to bounded input not worse than polynomial output. Exponential output, nope. Polynomial, yes. I had to change the definition in order to do differential equations because it corresponded physically to what I wanted to do. I didn't want to say my trajectory in the moon was unstable because it was coming into the moon properly all right. It was the nature of the problem. I was calculating accurately the nature of the problem. The problem was unstable, not the method. So I came up with very different definitions, and I want to talk about the matter. When a field of knowledge is extended to a new area, the old definitions are often inappropriate. I have found this again and again and again. Throughout the history of physics, for example, mass and energy were quite separate until Einstein came around, showed E equal mc squared, and suddenly the conservation of mass and conservation of energy were no longer separate ideas. It was the idea that the conservation of the sum of those with equivalence was constant. Again and again, we have got to change our definitions of what we mean as we get new problems and new techniques. The old definition will not work. I told you in the very first lecture on digital filters how the guys who were analog people tried to stick to analog approach and think the digital one was the same. They were wrong, completely wrong. They could not take a constant input and hang on to it and not have a drift without. On the other hand, I can put a 1 in a digital filter and 5 years from now it's a 1. You put a 1 ohm resistance in an analog filter and tomorrow it isn't 1 ohm. It's changed. Furthermore, they had heating effects and they had other things. A digital filter doesn't have those troubles. Those numbers are beautiful numbers. So long as the computer runs, those are the numbers. And there's no temperature compensation. There's none of all those crazy things. Or atmospheric compensation. There's none of that in the running a digital filter, which were true in the analog ones. And the coefficients in the machine stay the coefficients. They don't change. Whereas in an analog filter, you build it today, tomorrow, the constants have changed a little bit. And the next day they're a little bit further off. There was a whole different world which they didn't appreciate. I could get away with things like practically staying on my head and balancing because the numbers would not change. They could never have done it. So what they couldn't do, I could do. In particular, they really couldn't integrate successfully. They had very poor business of integrating filters. The best they could do was charge the condenser and try with a feedback amplifier to keep the charge in the condenser right. But the best amplifiers they could build, and when I was stuck with the analog computer, weren't stable over 10 minutes. We tried to get our solutions done about 2 or 3 minutes before the inevitable drift. But a digital machine, no, I can leave it sit there for 2 days and the numbers are still exactly the same. It was a different problem. So I had to change things differently. As I say again, this is a characteristic of all new fields. The main theme today has been exactly that. How what you learn one way has got to be fixed. The power spectrum was reasonable in the analog days, but when you go to fast Fourier transform, this is not the spectrum which you got in analog days. It is taking the interval, the delta t sampling size times the 2n number of samples you take, that period, everything is forced to be harmonic in that. You may have a perfect sinusoid, perfectly periodic, but if it isn't that period, you'll find it spread over the spectrum. More strongly nearby, but you'll find it spread over the whole spectrum. So what has happened is, to some extent, the spectral approach to science in general is fading. It's fading because I told you, one, they lost half the information. I told you why. It was because in the early days, phase didn't matter, the telephone company didn't do it, and the telephone company, being the chief developer of modern electronics, if they didn't do it, who else would? And there was a sacredness about Bell Labs, which shouldn't have been. People should have said, yeah, Bell Labs is all right, but come on, they aren't everything. We got different kind of problems. We're not doing voice. Why should I throw away the frequency? And I keep murmuring that to Tukey and other people about, yeah, every time you give me the spectrum, I've thrown away about half the information. What about the phase? Isn't that important in some situations? Well, the answer is, you're darn right. The phase is very important, frequently. In fact, we have systems now which work solely on the phase, and to hell with the gain. We've learned to use them. But it took a very, very, very long while. Working back and closing this lecture, which is the main purpose of the thing. Next time I'll take up recursive filters a little bit and tell you more. The main purpose of this lecture is to try and point out to you what I told you about the fast Fourier transform. The received knowledge developed in the past for past purposes, fitting past situations, was probably correct. It may not be correct for today, and is quite probably not correct for tomorrow. Now, in your business, I saw it quite frequently. Coming out of Los Alamos, and since my wife worked on the hydrogen bomb, I knew not only the atom bomb when I left, but I knew about the hydrogen bomb, which did not come up public for a long while. I saw various people in the military saying, oh, it's nothing other than a larger bomb, or, boy, it's the solution of everything. It was neither. It took the military a long time, and no one knows whether, in fact, they've digested or not, because, to my great surprise, I've lived this long without an atomic war going on. When I left Los Alamos, I didn't think I had 20 years before an atomic war would break out. So, you know, I was lucky. I've had almost 50 years. Whether it's actually been controlled, whether the military knows how to use it or not, we have no evidence. I saw the same thing with guided missiles. I told you how one of my friends spent a year down in Washington wandering around trying to tell people the guided missile will not do everything. It'll do some things, but not everything. It's better than a lot of things. It's got a lot of possibilities you haven't thought of, but it won't answer all your problems. The difficulty is everybody wants to be comfortable in their mind as well as their body. They don't want to think new thoughts. They want everything to fit into the old. A computer is nothing else than a desk calculator speeded up. Yes and no. Atomic bomb is nothing else than a big bomb, just bigger. Yeah, yes and no. Guided missile is nothing else than a missile, but a little bit of guidance. Well, yes and no. You are going to face that more and more. We have a rapidly evolving technology. The desire you have to put things in the background that you're familiar with is legitimate within reason. But those who think there's nothing new happening don't contribute to the future. Those who think there may be something new is going on here do. Your terrible problem is this something new, or is it just something old and people are claiming something new? Is there something really new? It's very hard. If you leap to every new thing that you're told is brand new, you won't do anything. You'll be jumping from here to there to yon. The taste of recognizing when something is fundamentally new and when it is something old with a new flavor, a new aluminum sheeting instead of steel or something like that, is a very hard thing for you to do, but that is a fundamental problem you will have to face in your career again and again and again. Is this a new thing, or is it the same old stuff with a new coat of varnish? Put again with a quit. If you think it's nothing new, you're not likely to contribute. If you think it is to be new, you're likely to spend most of your time chasing something that's not there. But it's the only way to be the leader. So I see you Friday. Oh, no, Thursday. Thursday, okay? We'll get rid of these digital filters.